Today's podcast is sponsored by Datadog, a monitoring platform for cloud-scale infrastructure and applications. Datadog provides dashboarding, alerting, application performance monitoring, and log management in one tightly integrated platform so you can get end-to-end visibility quickly. And it integrates with more than 350 technologies, including AWS, PostgreSQL, Kubernetes, and Docker. You can visualize key metrics, set alerts to identify anomalies, and collaborate with your team to troubleshoot and fix issues fast. Try it yourself by starting a free 14-day trial today. Listeners of this podcast will also receive a free Datadog t-shirt. Visit bit.ly.com/DatadogShirt. That's bit.ly.com/DatadogShirt to get started. This is Scott Hanselman. This is another episode of Hansel Minutes. Today I'm talking with Scott Shawcroft. Two Scotts on the show. He is the lead of CircuitPython and works for Adafruit. How are you?
I'm great. How are you?
I am a fan, man. I'm a fan of yours because I watched you kind of talk about building cool stuff in CircuitPython, but then you built something that was even cooler. You bridged CircuitPython with a Game Boy.
I have,
which was amazing. And I got to meet you in person and see it, and it's real and it's wonderful.
Yeah, hoping to make it more real in the future. I just need to get back to fixing some of the bugs and getting the Game Boy Color sorted out, and hopefully actually get it on sale at some point.
So let's back up and talk about what CircuitPython is and where it came from, because I've got a bunch of things on my desktop here. I've actually got, you can probably hear them. I've got a bunch of boards. These are all Adafruit boards. You can go and buy all kinds of different things. How many boards does CircuitPython run on?
I think it's at least 60 at this point.
Oh my goodness. And some of these are cheap. Like these are like necklaces.
Yeah, the least expensive I think is about $9 or $10 US. That's the trinket.
Yeah, so those are small, and the trinket has some sensors and some lights, and you can turn it into
the Circuit Playground. Yeah.
The playground. What does the trinket do?
The trinket is very small. It only has maybe 10 pins total.
But here it is. I've got that one.
Yeah, it's really, really small, and it's very good if you have like one thing that you want to do, and are space constrained.
It's like the size of a quarter almost.
Something like that.
Yeah. And I've also received, I'm a subscriber for the Adafruit Ada box. You should definitely go out and Google for Ada box. It's just a happiness box that shows up every once in a while. It's the best subscription. We canceled all of our newspaper and magazine subscriptions, which were $10 here and $10 there.
Right.
We got the Ada box, and the 11-year-old and the 13-year-old go running when they hear it's on the way.
Sweet.
And every box has something fun in it. And the last one had basically like it's a CircuitPython based, almost like a Game Boy. It's a little, little NES kind of a deal. It's got controllers up, down, left, right, and a color screen, and it runs Python.
It can run Python. It's not the only thing it runs, but it does run CircuitPython as one of the options.
Is that a common idea with these boards? They can run Python, but they also run.
Yeah, totally. Like Adafruit is a hardware company, so they're happy to see you use the hardware in any way that you choose. We are open source hardware and open source software, so you can put whatever you want on it. We're happy to see you make things with the things that Adafruit makes.
So these boards can be Arduino boards, and we can program them with Arduino, or they can program them with Python.
Or Microsoft MakeCode is another option as well, which they've done amazing work on the gaming side. So they have MakeCode Arcade, and that's really much more fleshed out than the gaming side of CircuitPython at this point. So it's worth a look if you haven't taken a look.
So I understand the Arduino part. I understand the idea of writing a C or C-like language on a board that's small, but Python's higher level. I mean, is there a runtime? Is there a Python runtime on this thing?
Yeah. So to take a step back, CircuitPython is a re-implementation of Python that runs on small embedded microcontrollers. They're very small CPUs. They tend to be about 48 to 120 megahertz is what we run on. And they have anywhere from 32 kilobytes of RAM up to 192 kilobytes of RAM. So much smaller than even what your phone has. And we're based on a project called MicroPython. They did a lot of the initial work to get the Python experience on embedded microcontrollers. And 3 years or so ago, Adafruit came to me and wanted to get that running on their hardware. And in those last 3 years, we've just made it easier and easier and more powerful in the ways that we think really help beginners. And that's our core audience is beginners.
When I got started with hardware and open source hardware, I thought about Raspberry Pis, and I would go and boot up an entire operating system. That's not a microcontroller, right? That's a microcomputer,
Microprocessor, yeah.
Microprocessor.
Yeah.
Okay. And that's a full PC basically. I mean, it's a whole universe there. It boots into an operating system.
Yep, it's running full Linux.
Okay, but with a device that is a microcontroller, I'm not booting into like a full operating system of Linux, am I?
No, generally not. Linux requires some memory fanciness that that microcontrollers tend not to have. You can get things called real-time operating systems that are designed for microcontrollers, but we don't actually use a real-time operating system for CircuitPython either.
And when I created my little things on Raspberry Pis, my batteries would only last for hours. But when I do my things with these little CircuitPython devices, these little tiny devices, they last for days or weeks or longer.
Hopefully. Yeah.
How is that possible? Help me understand that differentiation between a microcontroller and a microcomputer. So when someone's listening to the show, they're thinking, well, I thought tiny hardware was only Raspberry Pis, but there's a whole universe of hundreds of boards. And like you said, over 60 that support CircuitPython that they can get at Adafruit.
Right. So there is some detail that draws that line between microprocessor and microcontroller. I think it has to do with having a memory unit that allows you to have virtual memories for different programs. For a microcontroller, the software that you're writing has access to all of the memory. There's no kind of boundaries there to isolate code.
I don't know if it's correct, but the way I've been explaining it to my 11-year-old was that a microprocessor like a Raspberry Pi can do lots of things all at the same time. And a microcontroller, you kind of think about it as a one program at a time. Even though the program can do multiple things, it's a single tasking. Like not single tasking in a computer science sense, but like I want this to control the garage, and now I want it to go and make an Iron Man hand. Those are two separate tasks.
And they're very, very common in kids' toys. And like I have a MIDI keyboard, and I've opened it up, and it has very similar class. In fact, we could run CircuitPython on it. It has the specs that we need in order to do it. So lots of the devices that you don't think have computers around you have little microcontrollers in them to do basic things like, let me see if buttons are being pressed, and if buttons are being pressed, let me do something based on that.
How did people do these things, and what code did they write before an implementation of Python that was this small existed?
Right. So Arduino was the big kind of democratizing force that happened. Prior to Arduino, my understanding, this is kind of before me as well, but my understanding is that in order to get into this class of hardware where it's really inexpensive on a per like chip basis, because it's in a bunch of devices, you would have to have a pricey device to program that chip. Now, Arduino did a number of things that made it much more accessible, but one of them was changing the way that you load the code itself, where you didn't actually need anything besides a UART or like a serial connection to load code. No expensive programmer. So that was kind of the previous decade before kind of Python and MicroPython and CircuitPython came on the scene.
Yeah, when I tried Arduino many years ago, being able to plug it in to a USB port, but have it show up as a COM port meant that it was super easy to talk to, and it was all virtualized. Once I didn't require a driver for anything, that's when I felt like this is actually worth the hassle. While flashing firmware was custom drivers, and that basically it was irritating. It was irritating enough that it was, for me as a hobbyist, no fun.
But still with Arduino, it required you to have the Arduino IDE because it built the software you were running and then pushed it to the device. Now, one of the things that MicroPython has done and CircuitPython's made even better is the fact that the tool chain's on the device itself. So when you plug in a device that's running MicroPython or CircuitPython, it shows up as a USB drive with the source code itself on that drive. So the source code, the human readable version of the code, goes with the device itself. So I could create a program for you and hand you the device, and then you would have the source as well. And one thing that we've added that MicroPython doesn't currently have or hasn't had is that when you save that file again, CircuitPython will actually reevaluate it immediately or nearly immediately. So what you'll find is that, like, if you're saying in your code you want to turn a light on, you hit save, the light will turn on immediately. You don't have to go anywhere else to say, hey, reload. It does it automatically for you. And it makes it very, very quick to experiment and see what happens based on the code that you've written, which is the holy grail of what we're going for.
It really is. And I know that this will sound like some kind of an advertisement. It is only my enthusiasm. I have no advertising relationship with Adafruit. I just am a fan. It is, as someone who, tried, again, many years ago, and still you can do this today, like get a custom device, install custom drivers, flash firmware. Then next step, use Arduino, do the comport thing, do the compilation locally, and then push it. Then next step, and then just plug in a device with a USB cable I have lying around. Like, I love the Circuit Playground and the idea that I would plug it in, and when it popped up as a drive, I was like, wait, what? And there's like a file there that says code.py. And I was like, I didn't even know what I was doing. And I opened it up in Visual Studio Code, and I got IntelliSense, and I hit Control S, and then the light starts flashing, and then it worked. And I was like, this is not possible with what's happening.
Yeah. I mean, that's a lot of what we focus on is what I've been calling the first 5 minutes. So what is your
first 5 minutes?
What is your first 5 minutes ever programming, right? Like, those are the people that we're designing this for. We're designing it for the person that knows that they want to try to code something. Like, they don't know what Python is. They just know that they want to code something. And that's why the file is named code.py, because that's become the term that people associate with the activity. And how quickly and how seamlessly can we get them to that point where they see that they've written code that changes what happens on the device that they're using?
It's so empowering. My 11-year-old was able to do this. Like that 5 minutes, people want it done immediately. It's like, hey, everyone, let's install this tool chain.
Right.
No, I don't want to do any of that. I don't want to install anything.
Yeah, I was thinking about our experience at PyCon, where we had a room full of people who wanted to try it. We gave Circuit Playground Expresses to everybody at PyCon, and we had what are called open spaces, which is just like, hey, for an hour, we're going to be in this room and we'll help you out with it. And we had like a double-sided 8.5 by 11 of instructions, and most of the people in that room got through all of the instructions there in an hour, which for kind of a workshop setting with hardware is just unheard of. Where people are using their own devices and like getting going, and it's just amazing to hear people making the noises and making the lights flash all different ways, and then they get creative and they do something that's not on the sheet, and they're just like glowing. It's really what we're going for, and the challenge is continuing to keep that focus on the first 5 minutes, because although everybody only has their first 5 minutes once, all of that investment in making it easy pays off for everyone, right? Like, advanced programmers like myself benefit from having a workflow that is that quick.
Right.
And that's why it's really a good thing to focus on the beginners, is because the benefits trickle down to everybody who's using it.
The phrase that we use in the developers tool division at Microsoft where I work, we call it the developer's inner loop, not the outer loop, but it's the inner loop. It's how quickly can I make a change and then see the change?
Exactly.
Is it one hotkey? Is it two hotkeys and then hit F5 and then hit a breakpoint and then wait? Do I have to just? You've taken hardware and almost turned it into like hitting F12 in Chrome and hitting refresh, and even less. You have one less click than that.
Yeah. Well, the auto reload based on the file save thing came from MicroPython was very much using what is called the REPL. It's the read eval print loop, where you can connect over the serial port and type Python and hit enter, and it will evaluate it. And we said, this is really powerful, right? This concept of like, I can type something in and immediately see its action is really powerful. And I I understood that, but I also dislike the REPL interface because the code you write doesn't live forever, right? Like once you
it's not
write it, you
persistent.
can't access it very easily again. It's ephemeral. And I was like, if we just auto reloaded on save, we would have the same instant feedback loop, but with code that stays that you can build on, which is kind of why we went that way.
When you hit save and there's a beep and a reboot and it feels like a reboot. I'm just saying reboot, but how is that not corrupting any files? Does the drive disappear? Like how does that work so reliably?
Well, the goal is to be reliable. We're not always. But the secret is that it's not restarting the whole thing. It's not restarting the whole microcontroller. So we're preserving your USB link. We're preserving your file system for you. What we are restarting is the virtual machine part of CircuitPython. So all of the memory that Python has touched will get wiped and restarted. And then we're also good about resetting all of the peripheral hardware that you may have used for different devices, like I2C and SPI, for example. We'll reset that in between reloads as well.
Okay, so it's a warm reboot, not a cold reboot.
Yeah, basically. And one of the challenges with this has actually been teaching people to not do a hard reset, because most of the boards have reset buttons on them, and that will start the whole thing over again, and you'll lose USB and you could corrupt your file system. So we've had to be very careful in how we talk about it, because the button's labeled reset, so the file system is an auto reload thing.
Okay, that's a good reminder to me. I don't want to just get into a habit of hitting Control S to save and then hitting reset, because it's just not necessary to hit reset.
Yeah. You shouldn't ever have to hit the reset button at all. And if you are going to hit it, you should always eject your file system and make sure that your host computer has written out everything that it thinks it needs to.
Hi, friends. As a programmer, you think in objects. With MongoDB, so does your database. MongoDB is the most popular document-based database built for modern application developers in the cloud era. Millions of developers use MongoDB to power the world's most innovative products and services, from cryptocurrency to online gaming, IoT, and more. You can try MongoDB today with Atlas, the global cloud database service that runs on AWS, Azure, and Google Cloud. Configure, deploy, and connect to your database in just a few minutes. Check it out at mongodb.com/atlas. That's mongodb.com/atlas. So you've got this wonderful high-level language in the form of Python, but you've got absolute power and control over these devices. I mean, you can go down to voltage, you can go down to pins, you can be almost like C, and you can call, extern C libraries.
It takes more work so a lot of the work that I do is actually written in C. So there's a lot of modules. There's modules you'll find like bus IO or digital IO. Those are actually written in C under the hood. Anything that talks to the hardware has kind of a C component to it. My job...
I have not seen that, though. You've hidden that from me as the user with the 11-year-old child.
Exactly. And that's the goal. The goal is that you don't need to worry about that. You also shouldn't need to worry about concurrency at all, because concurrency is tricky, even for me.
It's not also no fun.
It's really tough. So my job is to focus on keeping it easy and keeping it simple and keeping it consistent across all of our APIs and all of our workflow and interactions and stuff. It's a challenge, but it's very worth it.
That's the fun side. That's the fun high-level side where you don't have to think about the internal details. You have made a wonderful layer of abstraction that's enabled me as a hardware dabbler, but not a hardware expert, to do a lot of damage with my kids, and it's super fun.
That's the hope.
People should get these. I want to shift, though, and I do want to talk about the low level.
Okay.
Because I want to talk about this Game Boy thing that you've made here.
Yeah.
Because it seems like the ultimate kind of like, in my left hand, I have Python, and in my right hand, I have like the lowest level possible way of thinking about computers. You're fooling the Game Boy somehow? I mean, the Game Boy itself is not running CircuitPython, right?
Correct.
Walk me through this. What have you made?
Yeah, so I just spent the last 10 minutes talking about how CircuitPython makes hardware accessible. And
Mm-hmm.
I wanted to prove the point that that can work for hardware that exists as well. You can do homebrew Game Boy games, but like a lot of the stuff we talked about, there's a lot of kind of esoteric programs that you have to install for it. And I was thinking, I watched this video about how the Game Boy works, and I was like, you know what? Which I guess is the start of a lot of my projects. But it's like, what I can do is so there's this notion of security that's basically like, if you have root access, you can do whatever you want, right? So like
Right.
once the CPU is in a privileged state, you can execute whatever code you want. You can do whatever you want with the device. And the Game Boy is 30 years old, and it has one little bit of security, but besides that, once the cartridge has control, the cartridge can create code to do whatever it wants. Game Boy games traditionally are just memory, so the code that embodies what Donkey Kong is just encoded in bits on a cartridge. But there's actually no restriction as to how those bits are generated. So what I've done is I run CircuitPython in the cartridge itself. And when the Game Boy says, hey, like either give me data or give me the next instruction I should do, I can just return it and say like, hey, do this instruction. And that gives me, I can do whatever I want as a result of that, basically. So I can do things like say, hey, I want you to write a piece of memory at this address, which happens to be the address that will play a sound on the Game Boy. So I say, here's the address, here's the piece of data I want you to put at that address, and out comes a sound from the Game Boy. And then I've plumbed that capability of setting the memory of the Game Boy into Python so that you can say from Python, hey, play me a sound on the Game Boy.
Okay, so let me see if I can paraphrase and understand this. The Game Boy, as you said, 30 years old, 1980, 1989,
Yep.
has a 4 megahertz processor, so certainly not something that could run Python, perhaps. That would be a fair statement.
Yes.
And
yep.
You would not want to have it run something itself. It's 4 megahertz. It's nothing.
Yeah, that's debatable too. People debate whether it's 1 megahertz or 4 because the memory bus is actually only 1.
Oh wow! Okay,
so it's only fetching one instruction, like at a 1 megahertz rate, one megahertz rate, not 4.
Okay, so that's so it's even 4 times smaller. It's 4 times weaker than I thought.
Yeah,
but there are 100 million of them out there, and
yep.
So then you run, like we mentioned, how one of the CircuitPython devices is as small as a coin. Certainly, lots of room inside of the cartridge. So you go to Goodwill, you buy a couple of copies of the Olsen Twins game, and you pop them open. You put the CircuitPython board inside, which has 100 megahertz, 200 megahertz.
120 megahertz is what I'm using.
Okay, it runs CircuitPython. It is communicating with the Game Boy only via the pins, the pin out on the cartridge.
Correct.
And so you've got voltage on those pins.
Yep.
And the Game Boy goes looking for memory.
Right. It says, hey, what's
ready to lie.
What's the instruction here? I need something to do. And I say, well, for now, just don't do anything. And then, one, what is it, nanosecond or 1 microsecond, whatever a megahertz is, like it'll come back to me and say, okay, now what do you want me to do? And I'll say like, oh, now I want you to do this like load thing that causes it to play a sound. And I just continue to do that over and over again.
That's so cool. When I think of the cartridge, though, it's a moment in time. It's a ROM, right? It's a bloop, here it is. There's the program.
Right.
But you don't know what's going to happen. Yours is kind of like, I wouldn't say non-deterministic isn't the right word, but you're lying to it constantly. Every instruction is a lie.
Right. So in a traditional cartridge, if the Game Boy CPU fetches an address, a particular address, it expects to get the same result over and over again. But it doesn't actually verify that is true, which means that even if it's like most of the time I can ignore what the address is, and I could just say, okay, now do this. Okay, now do this. And the Game Boy CPU doesn't care and and we don't care either about the addresses almost
Really? I see. So
entirely.
it's not saying, well, hang on, that's not what you said earlier. That's not an appropriate thing to say at all.
Right. So
It doesn't care.
So more modern systems, I think, would be more trouble in that regard. But the Game Boy CPU is simple enough that it doesn't have any caches, so that like if it was trying to remember what was somewhere, and like they would have like consistency problems and stuff, but it doesn't do that. It doesn't need to because cartridges are relatively quick. Reading straight from memory is pretty quick. It's only when you get to like CD-ROMs where you have to, or spinning disks, that you can really incur a lot of time.
How do you debug this? When I work on hardware problems, I always have this feeling like at some point it gets to a black box, and it's not really a black box, but it's a black enough box that without an oscilloscope, I don't really know what the waveform looks like, or I'm sitting there with two wires trying to figure out if there's voltage on that pin. How in the world would you do anything other than just, I don't know, piss off the Game Boy and make it crash for hours and hours?
Well, I've done that. I've definitely crashed it. In fact, we just, right before we met you at Teardown, my buddy and I were working on making it crash less. And we realized I was accidentally issuing the instruction that tells it to stop. There's a stop instruction on the Game Boy, which turns the screen off and basically the CPU off as well, just waiting for you to press a button. So if you press a button, it all wakes up and it starts up again. But I was accidentally doing that. And I thought it was like really crashing when I was really just telling it to stop accidentally.
How did you learn that though? Did you learn it with a voltage meter or voltometer? Did you learn it with a debug statement? I'm trying to get my sense around how do you debug something like that?
I have a logic analyzer. So it's kind of, you're connected to a bunch of the pins so the cartridge connector itself is like 32 pins. But my logic analyzer can only do 16 at a time. So I've selected bits of the address and bits of the data so that I can see what the Game Boy is requesting and what we're giving it back. And so we realized like, oh, we're like on the logic analyzer software, we could see like, oh, this is the data that we're returning when it's asking for an instruction. And that instruction, we looked it up and it said stop, which was bad. So yeah, in general, a lot of video game systems are really well documented because they've been emulated a bunch. So there's a really good PDF that you can find called the Unofficial Game Boy CPU Manual. It's, I don't know how many pages, but it goes into great detail about how the Game Boy actually works. So there's a lot that is already known. Only a few people that I've found have actually tried to make cartridges like I have. But in general, most of the things that you need to know. The challenge is kind of like bridging that gap and making sure that you can respond in time, for example, or if you are trying to issue instructions to the Game Boy, making sure that once you give an instruction once, you don't give it a second time accidentally. You need to make sure that you get the next thing there in that 1 megahertz window that you've got, which I think is the source of some of my problems right now.
And that idea that you have to, the timing, like as old as a device as this is, it is a sensitive piece of hardware such that if you're not ready X microseconds later, then you weren't ready. And now you have to wait another clock cycle to come back. And if you really waited too long, you're going to really anger it, aren't you? You're going to
potentially, yeah. Potentially what you'll do is you'll issue an instruction that does something that you didn't intend. And if you do that, you potentially lose access to the CPU. If it's trying to run code from a different part that is not on the cartridge, you could potentially never get called back. It could never actually read the cartridge memory anymore, which is kind of the worst case.
So the Game Boy part, like, shut up, take my money. I'm right there with you.
I know.
But
I need to work on it.
Well, there's that, but it feels like you've created a generalized, and I call it left hand, right hand, where you've got Python on the one hand and some older piece of hardware on the other end. You could potentially take this how far? This is a great way to revitalize all kinds of hardware with this buddy cartridge stuff.
Yeah, whenever you're in Seattle, you'll have to come see my laundry room because I have collected a lot of different devices that kind of fit in all of this same era. of cartridge based computing systems like Commodore 64, Atari 800, Apple II. Doesn't have cartridges, but they have PC like parallel slots that could work the same way. And they're all kind of pre-security and validation. So we should be able to play similar tricks to the memory. Even if there are caches that are trying to remember what was there, we could always, like once we have instruction access, we can always turn those off, hopefully. So that it doesn't, we don't need to worry about that consistency issue. So there's a whole lot of stuff that you can do that with. Another example is like 80s era piano keyboards. I've been interested in. So I have an old Yamaha keyboard, and the sound chip that does the synthesis is actually the same one from the Sound Blaster, the original Sound Blaster card, which is like a super classic sound. And I want to be able to put CircuitPython in that and control all the playback from CircuitPython. So you could have USB MIDI coming in and playing your keyboard, or the vice versa, where you're playing on this 80s era keyboard, but you're streaming MIDI back up the link to your over USB as well. It's just, possibilities are endless, and I wish my time was endless as well, but it is not.
I was thinking about something that I wish I had the skills to make, which was, yes, you've got cartridges on something like a Commodore 64, but there was a whole class of devices that would take information from a tape drive, where you were effectively a one-way modem. Like, people don't realize that it was almost as if you had recorded a modem noise and you played it back over tape. Could you make a system that lied and made that noise, and as if it were a phone call that never ended, and you would just keep whistling, and you'd have your CircuitPython device, send those instructions down the wire?
Yeah, you could, but I think what you would run into is that the computer expects those devices to be very slow. And I think the way that those typically worked is that because they were slow, they would have to load everything into RAM and then run from RAM. And so you wouldn't necessarily be able to do that sort of like dynamism that I have with the Game Boy, where I'm constantly changing the program that I'm returning to them based on what the program I'm running internally is actually doing. I think you would have more trouble with that.
So the cartridge-based model, you want to see how far you can run with this, and it sounds like you could potentially run pretty far. You're limited only by your time and perhaps the interest of other people in the community who might be interested in helping.
Yeah. I mean, we're always looking for contributors to CircuitPython, whether the Game Boy era retro stuff is interesting to you, or who knows what. One thing I'm very excited in the workflow vein, going back to that, is we're starting to really, our Bluetooth low energy support is starting to mature a lot. And what I've found with my nieces is that they all have iPods or iPads before they have laptops. And though I don't know about your sons, but the mobile devices are what kids are starting with and having as their own. And so I really want to make CircuitPython, that workflow that we have over USB, work from a mobile device in a wireless way. And that's kind of the challenge towards the end of the year, and probably going forward in the next few years, to make it really solid. And that's my day job. So I will have time to do that as well.
That's so exciting. Well, thank you so much, Scott Shawcroft, for chatting with me today.
Thanks for having me.
You can check out everything that he's working on at tanewt.org. That's TANNEWT.org. And I'm a huge fan of the Ada Box, the Adafruit curated collectibles subscription service. Check that out at adafruit.com/Adabox. And also go check out all the great CircuitPython boards and fun things that you can do at CircuitPython.org, as well as the products at Adafruit that support it. This has been another episode of Hansel Minutes, and we'll see you again next week.